Okay, so this video is going to explore the second law of rotational motion, which is based on the second law for translational motion. And it's very helpful when we're trying to transition from the translational way of looking at things to the rotational, to remember what it says. You know, what does the second law actually say about translational motion? This law is pretty simple. It's essentially explaining what causes the acceleration of objects. So the acceleration depends on two things. Number one, it depends on the net force. It's a direct proportion for that, meaning that if I double the net force, I will double the acceleration. But it is inversely proportional to the mass. What that means is that for a constant force, if I increase the mass of the object that I'm applying that force to, I'm going to get less acceleration by that same proportion. So inversely proportional means doubling the mass would result in 1/2 of the acceleration. So the equation is essentially saying this, that A is equal to F net over m, right? So this is the way that Newton envisioned a way to actually mathematically calculate the force acting on an object. This defines that force is equal to ma, but really important to understand that the acceleration of an object depends on the total force, or the sum of the force, or the net force, not the individual forces. The individual forces combine together to produce a net force, and that is what is going to determine the acceleration. Now, as you've seen before, the way we get the net force is if we know ma, we can just calculate it that way. But if not, then we need to add up all of the individual forces. So when I add up all the individual forces, that will determine whether we get acceleration or not. If the forces add up to be 0, that's the first law. We don't get any acceleration. If they don't add up to 0, then we do get acceleration. So the idea is the same behind rotational motion, except that instead of saying A is proportional to, what we would say is the angular acceleration, so not the acceleration, but the angular acceleration of an object is directly proportional to the net torque, because torque is what causes rotational motion in the same way that force is what causes linear motion, and it is inversely proportional to the moment of inertia, not the mass, right? So again, with rotational motion, it's a little bit more complicated because we have to think about where is the mass located? How extended is that mass? The more extended the mass is, the larger the moment of inertia, the harder it's going to be for you to make changes to things. So objects would have their weight way out at the edges of the rotation are much more difficult to move than objects that are very close. So what the equation is saying is that the angular acceleration is equal to the net torque divided by the moment of inertia. And in this case, it would be helpful since these are new. Let's make sure that we remember the units for all of these things. So alpha is going to be in radians per second squared. It's an acceleration. I is the moment of inertia, and this is a kind of a new property. That is going to be in kilogram meters squared. We'll revisit that in just a moment. And then finally, the torque is going to be in a couple of options. It could be either kilogram meters squared per second squared or Newton meters. Now just realize both of those are units of energy, but they are not energy because it is not the right lever arm, the distance. The displacement that you would use normally to calculate work is a different displacement than what we're using here to calculate the torque. Remember, torque is times the lever arm. It's not how far the force was applied over, it's how far away the force is from the point of rotation. So just in the same way as that we took this equation and we created a working version. This is the working version of the translational motion second law equation. We would do the same thing for this one, and that would say that the net torque would be equal to I times alpha in the same way that the net force is equal to m times a, and then that would simply be a sum of all of the individual torques. Okay, now we have not spent a lot of time talking about this, but at this point now we do need to address this idea of the moment of inertia. Okay, the moment of inertia is simply a product of the mass times the square of the distance between that mass and the point of rotation. Okay, or the center of mass of the object. But it can be measured in different ways. So ultimately, we would say that I is equal to the sum of m times r. So essentially, each individual atom, we would figure out what its mass is. We'd figure out how far away is it from the axis of rotation, and then we would square that distance and multiply by that mass, and we would get the moment of inertia for that atom. And then if we want to know, well, what's the total moment of inertia for an object, then we would have to add up all those moment of inertia. Now, it's not really very feasible to do something like that. But using calculus, we can derive for common geometric shapes, we can derive what the moment of inertia would be depending on what the shape of the object is, and also, this is super important, depending on how is it rotating. So for example, this object, this pen, I could rotate it around the center of the pen like this, or I could also rotate it around the end of the pen. And it actually has a different moment of inertia because if you just think about it, there's much more mass far away from the point of rotation in this situation than there is here. This has a smaller moment of inertia because all of the mass is much closer to the point of rotation. Now, no point on this pen is more than half the length of the pen away from the point of rotation. But if I choose this end over here and I make the rotation around here, now I have much more mass. This mass over here, which was previously only about half the width of the pen away, now it's the entire length of the pen away. So you can imagine the R is much larger. So when I multiply that R squared by that mass, I get a much larger moment of inertia. You will never have to do something like that. Okay, now conceptually you should understand it, that the moment of inertia is the combined sum of all the individual parts of the object multiplied by the square of the distance from the axis of rotation. But you will simply be given them, or they'll give you a list for common shapes. So if you look in the book, either the books that we use, the Giancali book, the Glencoe book, or really in any physics books that talks about rotational motion or angular motion, you will see a page which gives you a list of about 5 or 6 common shapes. That's going to be like a sphere, a metal rod, a circular disc, a hoop, a solid plate. It's going to give you some simple geometric figures, and all you need to do is match up your geometric figure, whatever it is that you're looking at, to the right formula to give you what is the formula for calculating the moment of inertia. And we're going to do that for an example problem. So let's make it a little bit more concrete by taking a look at the first example problem. The first example problem, what we're looking at is a belt. So in this case, we're talking about some kind of disc around which a belt is wrapped. So as the belt is pulled, it causes this wheel to rotate in this direction. And in this case, what we're talking about is a 14.5 kilograms, this is like a metal wheel, generally speaking, that is connected to a belt. Now, one thing about the force that the belt applies, this is a friction belt. This is all over the place. In your car, there's all kinds of places where there are wheels or pulleys or things like that that are driven. It's just by friction. The frictional force is going to be parallel to the surface. So that means that the frictional force will always be in the right direction. That is to say that the frictional force is always acting sideways on the object. So we don't need to worry about the angle. So the sine of theta business, that's not really, it's not really a relevant thing for us to even to worry about. So we assume that the wheel is spinning, and it is spinning in a, that the wheel is spinning in a uniform circular motion. We can calculate the moment of inertia for this guy, even whether it's moving or not. Because this is a disc, essentially we have something that looks like this. Right, so we have a disc. You can look up in the book, and on the test it would be given to you, and it turns out that the formula for this one is 1/2 mr squared. So if I take the mass, which was 14.5 kilograms, and multiply by the radius, the r, in that case, the r for this one is the wheel. It's a pretty large wheel. It has a radius of 0.58 meters, so this is kind of a large disc. Times 0.58 squared, then we'll get a moment of inertia of 7.3167. Remember that the units are always going to come out in kilograms times the distance in meters, which was going to be squared, so it's going to be kilogram meters squared. That's really a new property. It is related to the mass of an object, but it's a different way of looking at it, and does have different units, right? Because mass would only be kilograms, and this is kilogram meters per second squared. So in this simple example, all we're going to do is we're going to try and figure out what is the angular acceleration of this thing. In order to do that, I do need to know what the torque is. Remember, we just saw this equation that said that torque is equal to I times alpha, but don't forget that we have another way of calculating torque, and that is F times R. The force times the lever arm, and as I said, the force is being applied sideways. The frictional force is always parallel or tangent to the surface of the disc. And so as a result, we don't need to worry about the sign of the angle. It's applying the force in exactly the way it needs to apply it to get the maximum amount of torque. But in this case, we can certainly calculate the torque for these two things. So the I in this case turned out to be 7.3167. I'm not reducing it down because this is not my final answer, so I'm going to save that and cut it down at the end to the right number of sig figs. On the other side, we have a force of 35 newtons, and that is being applied at a distance which is 0.58. It's being applied at a distance which is 0.58 from the center of the disc. So in this case, we would end up with an alpha equal to 2.77, and don't forget this is radians per second squared. So the acceleration of the object. Looking for examples where you'll use this idea of the second law, which says that torque is equal to I times alpha. That's the second law. And then also remembering that, of course, we always have the definition of torque, which is the force times the lever arm. We can set those two things equal to look for missing things, like what is the length of the lever arm, how much force was applied, what's the angular acceleration, or we could even use it to find the moment of inertia. That's certainly a possibility that you'll be asked to solve for the moment of inertia. Let's take a look at a second problem that's a little bit more challenging, because in this particular case, what we're talking about is a situation where while this force is being applied, this thing is going to exert an angular acceleration to the wheel. But let's take a look at one where we see things that are changing a little bit. So this is a piece of playground equipment from when I was young. I guess it's probably not very common anymore. You don't see it on very many playgrounds. When I take my kids, I just don't see this device very often. I imagine it's because so many people got hurt using it. It's a kind of device where you can take it up to really crazy speeds, and people can get thrown off of the thing. It's called a merry-go-round. There's other names for it, but generally speaking, most people would just refer to it as a merry-go-round. And in this case, we can see from the picture, there are two children. The two children are sitting out near the edge of this thing. I'm estimating what I think would be the size of this. This does not look like a particularly large one. So I'm assuming that the kids who are sitting on the edge are about 1.2 meters from the center, because that is the diameter, or the radius, I should say, of this device. In this particular case, since both children are sitting at the same distance from the edge, it's not going to really matter that we calculate them separately since they're both sitting on the edge. They both have the same lever arm. They both have the same R. So we won't need to worry about that. The kids have a total mass of 84.5 kilograms. And as you can see, one of their older siblings is pushing the merry-go-round. And I'm just making up a force. We'll assume that this person can exert 157 newtons worth of force. Now, before we can do anything with this problem, we have to calculate the moment of inertia. Now, the moment of inertia is a simple calculation when you have a simple geometric shape, like let's say a disc, which essentially the merry-go-round is a disc. So there's a flat base, which is most of the mass of this object. And I'm going to ignore the handlebars for this particular example. We're just going to look at the disc, plus the disc has two children sitting on it. So each of those two children produces an additional moment of inertia. The more people we put on this thing, the more difficult it's going to be for you to make the thing rotate. So in this particular example, we have two moments of inertia that we need to calculate. One for the platform itself, and as we just saw from the last problem, that is 1/2 the mass times the radius, so that's 138 times the radius, which is 1.22 squared, plus each of the children is sitting at 1.22 meters from the center of rotation. So in that case, it's not a formula. I'm saying there is mass, there's a point mass from this person, 1.22 meters from the center. So all I need to do is m times r squared. So that would be 84.5 times 1.22 squared. Okay, now when you make that calculation, you bring all these two things together. When you make it in your calculator, you should come up with an answer of 228.5. And this is again in kilogram meters squared. Okay, so a pretty large moment of inertia, much larger than the one we were looking at in the previous problem. So if you think about it, a situation like this, there's essentially two torques. One torque comes from the girl pushing, and the other torque comes from the friction. That is down here. So inside where the metal rod is connected to this thing, there is two metal rods. The one fits inside the other and allows it to rotate. But then, of course, although they put grease in there to allow it to turn more easily, it still puts a little bit of friction. And so that's our goal, is by measuring the angular acceleration of this thing. So they start from rest. She starts spinning them around faster and faster. The question is, what is the frictional force that is being acted on by this object? So the idea is that the net torque about this is I times alpha. Just realize that's the MA of the translational world. In the translational world, I would have said MA is equal to, and then I would have listed out all of the forces acting on it. In this case, the force that the sister is putting, and then also the frictional force. But here we're looking at rotational motion. So I'm going to say I alpha is equal to the torque. I'm going to say OC from the older child. So OC, the older child. They are exerting a positive torque. Okay? And then I'm going to say the frictional force is opposing the motion. And that's it. There are no other torques. Those are the only two forces acting on the platform, are the girl pushing from the outside and then the frictional force, which is much, much smaller. So in order to know the frictional force, we would actually need to know what the radius of that inner tube is. Where's that frictional force being applied? Much, much smaller. This thing is probably only maybe 10 or 15 centimeters wide. And so the radius is much smaller. So I took the radius to be about 6.2 centimeters. Seems pretty reasonable for the size of this thing. And so with that information, we're going to be able to go ahead and calculate this. So the I I've already got, that is 228.5. I was given the angular acceleration is 0.816 radians per second. That should say radians per second squared. The torque on the other side, she is applying a 157 Newton force at 1.22 meters from the center, minus F of F times 0.062. Okay, F times R minus F times R is going to give me the I times alpha. So on the left-hand side, we end up with 186.456. 157 times 1.22 is 191.54. Make sure you're checking these in your calculator. Go through these and make these calculations yourself. And that's going to be minus 0.062 F of F. So moving everything over to the other side, I'm going to move the 0.62 F of F over to the left by adding it. I'm going to subtract the 186 over to this side. I'm going to end up with 0.062 F of F is equal to 5.084. And therefore, when I divide finally by 0.062, when I divide by 0.062, I will end up with 82 newtons. Okay, this is a relatively simple, straightforward problem. Two forces are competing against each other. One of them is winning. It's producing an acceleration. The one complication is that we do have to calculate the moment of inertia, and we never had to do that before because we would just plug in the mass, whatever the mass of the object was. But in this case, I need the moment of inertia of this merry-go-round, which includes anybody who's sitting on top of it is included in that moment of inertia. So while there's a little bit of an extra complication to the problem, it's not super difficult. It's still basically the same idea as the simple second law problems. Very common to see two forces, or in this case, two torques working against each other to produce that angular acceleration.